Dear colleagues and audience, welcome to attend Professor Abd Visser's lecture at Wuhan University. First of all, it's our great pleasure to introduce the speaker tonight for the Chinese audience. This is a picture of Professor Abd Visser. Academic positions and titles. From 1998 to 2016, he was a professor of logic, philosophy of mathematics, and epistemology at the Department of Philosophy in Utrecht University. In 2005, he became a member of the Royal Dutch Academy of Arts and Science. In 2015, he obtained the title Distinguished Professor at Utrecht University. Education. He studied applied mathematics at the University of Twente from 1969 to 1974. From 1974 to 1976, he studied mathematics major subject and philosophy subsidiary subject at the University of Utrecht. His specialization was mathematics. The subject of his master's thesis was predictivity. From 1976 to 1981, he worked as a PhD student at the Mathematical Institute in Utrecht University. His PhD thesis is titled Aspects of Diagonalization and Provability. Fields of scholarship. His general interest is in logic, foundation of mathematics, and philosophy of language. His current research consists of several interconnected projects. Sorry, this is some maybe it's a symbol, so it cannot appear. First, the mathematics of interpretations, the incompleteness theories, the study of satisfaction predicates, logics for probability, and interpretability. Publications and contributions. He has a wide academic interest and has published over 90 articles in journals and connections. He has made important contributions to the general theory of interpretation, the study of incompleteness, and the mathematics of arithmetic. Editorial works and ASL services. I just list some in the time order. He was editor of the Journal of Symbolic Logic, editor of the Journal of Philosophical Logic, editor of the Review of Symbolic Logic. He was member of the ASL Executive Committee, member of the ASL Committee on Prize and Awards, member of the Golden Prize Committee, member of the ASL Nominating Committee. Okay, we give a brief introduction for the Chinese audience. Now it's time for Professor Abd Visser's lecture on essential hereditary undecidability. Please and welcome.
Okay, then we shall try to share screen. Okay, you're all seeing this, and now I'll try to do few full screen mode.
Yes.
Yeah. Okay, there it is. Good, very good. And does it also move? Yes. Okay, yeah, so I'm, thank you for the generous introduction, Jon. I'm very happy to speak again in this seminar. Yeah, and it was, of course, also about the kind of subject that I like. Yeah, so the idea of today's talk is that I really want to explain one result and one proof. So the main part is around, I think it was 20, something like 20 slides. But then I still have some extras. So, but I think the main thing is that I want to explain this one proof. And so please please feel free to interrupt me with questions questions about clarification. Since I think the real thing that we want is that I at least convey to you what the theorem is and what and the main ideas of the proof. Okay, so here you see the heroes of the present talk. So one of the heroes is Raphael Robinson. That's the one to the left. Then we have Alan Cobham. So unfortunately, I couldn't find a bigger photo of him. I think this was really the only photo I found. And then there's Robert Ford. Yeah, so Cobham is, I think, among logicians far too little known. My impression is that he really was a genius and had an incredible amount of deep ideas, but I'm also afraid that some of his great works are hidden in letters, correspondence, for example, between him and Tarski that we cannot access. Unfortunately, at least I cannot access it, since I cannot go to Berkeley and search through a number of big boxes of letters. Okay, so yeah, so the general area where my lecture is located is really the children, so to speak, of this first incompleteness theorem. So the first incompleteness theorem is quite interesting. Of course, Gödel proved something around 1930, and then people did things with it, and Gödel's result ended up in textbooks. But if you look in textbooks, it seems that the authors of the different textbooks completely disagree on what Gödel precisely did, right? So that if you look at the statements, Gödel's first incompleteness theorem, then you find a lot of things. So usually, at least, there is something like T, if suppose the theory is sufficiently rich and sufficiently sound, and then what those things means will differ for every textbook. And then the conclusion would be, for example, T is not decidable, or there is a sentence that is independent of T, or there's a pi01 sentence that is independent of T, or there's a true sentence that is not provable from T, or there's a true pi01 sentence that is not provable from T, or it's even the specific Gödel sentence is independent of T, and then often people also add that expresses its own provability from T. And so so most of these versions are what I would call extensional. So they don't quote any kind of internal property of the theory. Just the version of 5 here, the Gödel sentence that expresses its own provability, is intentional. And of course, then this intentionality is, at least for me and many other philosophers, a kind of fascinating subject, right? So how do you, in what sense can we take it seriously that the Gödel sentence expresses its own provability, etc.? So we are not going to talk about that at all. So I guess that the confusion in the textbooks is really a good thing, because it shows that there's many ways to develop Gödel's original work, and so you have a lot of improvements and refinements. So Rosser showed first to prove the sigma 01 soundness. So I forgot to say, in the literature, of course, there's even in quite recent textbooks, instead of sigma 01 soundness, they have omega consistency. I never understood why, except for the historical fact that Gödel used that, why people use that notion instead of the more obvious sigma soundness. Now, Tarski, Mostovsky, and Robinson, they addressed really this question about rich enough, and they showed that there's a very weak theory R, And if you start from that, then you already get the first incompleteness theorem. And then Kline also did a lot of interesting work, and he, among others, showed that you can derive versions of the first incompleteness theorem from things that can broadly be viewed as recursive theoretic facts. Okay, now if you look at the developments from the first theorem on, you see, I think that it's no exaggeration to say that the thing that stole the show is concrete or tangible incompleteness, right? So I think it was mainly Kreisel who pushed the question. So given that we know these independence phenomena, so are there real meaningful mathematical sentences that a mathematician would recognize as an important insight that are independent? And so there was this the search for mathematically meaningful statements, and that became a whole industry. And of course, it's all started with the Paris-Harrington theorem that states that PA does not prove a certain version of Ramsey's theorem. So I'm not going to talk about intentionality. I'm not going to talk about concrete or tangible incompleteness, but more about versions of the incompleteness theorems that are uniform, and also that are closely connected to recursion theory. And so the typical thing is for these uniform versions is that they study whole classes of theories rather than specific ones, right? So in tangible incompleteness, you have that the continuum hypothesis is independent of CFC. So that's about a specific theory, but so we are interested in whole ranges of theories that have certain behavior. Okay, so that's my introduction, putting the whole thing in a kind of general setting, I hope. And now we get the kind of the basic facts section that is intended to give you the necessary concepts. So we look at series in finite signature where these series are given by an RE set of axioms. So I think we don't don't take an index for that set as part of the data, but I think most of what I say will work for both interpretations of what the theory is, whether the representation of the sigma, the RE set, is part of the data of the theory or not. So I will write that U is a subset with a little s for same of a subtheory of V if both theories have the same language and the theorems of U are a subset of the theorems of V. Yeah, so in discussions with Young really likes to stress how important it is that it's the same language, and indeed it is. So it's a crucial thing for this talk that we keep in mind that we're talking about extensions in the same language and not just extensions in any extension of the language. Okay, now there's the first thing is the notion of essential undecidability. And that means that U is essentially the undecidable if for all consistent extensions we have that they are undecidable. There's always a little bit of discussion. Should we build in that U itself is consistent? Oh yeah, so I did it here, but other authors don't. But the strange thing is that if you don't build it in, that a theory could be essentially undecidable without being undecidable, which feels a bit strange. Okay, a consistent theory is essentially hereditarily undecidable if for all consistent extensions in the same language and for all subseries in the same language of the extension, we have that subseries undecidable. So the general rule here is that essentially is a quantifier over, really indicates a quantifier over super series in the same language, and hereditarily really indicates a universal quantifier over subseries in the same language. And so essentially hereditary undecidable means for all super series, for all subseries, we have undecidability. Okay, so yeah, so these notions essentially and hereditarily were introduced in Tarski, Mostovsky, Robinson, but so they never noticed that the notion that we are, so they noticed the notion that we are studying, but they never noticed the systematic name for it, that it's essential hereditary undecidability. Yeah, so this is the systematic name, but you always think of the thing in a different way. Namely, you say that a theory is essentially hereditarily undecidable if whenever W in the same language is consistent with it, it's undecidable, right? So that's the important notion. And you see that, so this notion of essential hereditary undecidability is a kind of very strong notion, a very strong kind of undecidability, right? So it's not only that you're undecidable, but you also contaminate every theory in the same language that is consistent with you with that undecidability. So it's a kind of highly contagious form of undecidability, you could say. Okay, so so there's a few kind of basic facts about these things, and the first insight is extremely simple, but it's kind of very important to have it always in mind. So the thing is that if you have a decidable theory, then every finite extension of it is also decidable. And the reason is simply that if the finite extension proves with phi proves psi, then the theory itself proves phi implies psi. And so since U is decidable, we can decide whether or not it proves phi implies phi psi. And for that same reason, we find that that we can decide that U plus phi, whether or not it implies psi or not. So that's very pleasant. It's complete triviality, but it's a kind of central thing that plays a role in this lecture. And that's from this we immediately get an important corollary, namely that if we have a finitely axiomatized theory A, one and too much here, and if it's also essentially undecidable, then it's essentially hereditarily undecidable. Okay, so here's the proof. So suppose you have a theory in the A language, W, that is consistent with A and that is also decidable. Then, since A is finitely axiomatized, we would find that W plus A is decidable, but W plus A extends A. And since A was essentially undecidable, then W plus A should be undecidable. There we have a contradiction, and so W cannot be decidable as we assumed. So that's it, right? So every essential undecidability and essential hereditary undecidability coincide on the finite series. Was there a question? Okay, so one thing that we will now and then use in our presentation, but not too much, I think, is interpretability. So I'm not going to really explain what that is. But an interpretation really is something that is based on a translation. And And then you ask that whenever the interpreted theory proves phi, then phi, the interpreting theory, proves the translation. And we are not looking at just any old translation, but we demand that it commutes with the propositional connectives. And we also demand that it commutes with the quantifiers, but so all the subtleties are in this commutation with the quantifiers, because the question is what does that precisely mean? And so because we do allow, for example, that a variable will be translated into a sequence of variables, and we allow that the domain of quantification would be relativized to a definable domain in the interpreting theory, etc., etc. Right? So precisely the interpretation of the quantifiers and also then the corresponding interpretation of free variables. That is where all the work is to really define this whole notion of interpretation. And good examples are, for example, the Beltrami-Poincaré disk model of hyperbolic geometry. That is really an interpretation of hyperbolic plane geometry in the Euclidean plane. Then there's the well-known interpretation of PA and ZF using the finite von Neumann ordinals, and the interpretation of the Euclidean plane in the real line. And so here you see, for example, if you interpret the Euclidean plane in the real line, you need pairs of points to interpret points in the Euclidean. You need pairs of real numbers to describe a point in the Euclidean plane, right? So that's a two-dimensional interpretation. And we write V and then the right pointing triangle U for V interprets U. And so, so to use this whole notion of essential hereditary undecidability, you really need the following version, right? So it says a consistent theory is essentially hereditarily undecidable if and only if, for all consistent V that interpret U, and for all W that are a subset of V in the same language, we have that W is undecidable, right? So U need not be present in V literally as a subtheory, but it only needs to be present modulo interpretability. So I think that's the important thing. And so this is the useful version. And for example, Tarski proved that group C, this is the elementary theory of groups, is undecidable by showing that a theory that we will discuss in a moment, Q, is essentially hereditarily undecidable, and he showed that there's an extension of group theory that interprets Q, and that then implies that group theory is undecidable using this theorem, right? So you see that this notion of essential hereditary undecidability, apart from its great interest in the sense of pure theory, is also a very useful notion for all kinds of applications. So what we also will need is, in the rest of the talk, is witness comparison. So the whole idea of witness comparison is that it's simply a syntactic notation, right? So when we have two formulas where the main connective is an extensile quantifier, then we write that the first one is smaller than the second one if the first one is witnessed before or at the same time is witnessed before, strictly before the other one is witnessed, right? So that says that we have a witness of this, and before or at the same time we do not have a witness of beta. Then we have the smaller or equal, and that's the same thing. So note that, because this is really kind of negative statement, that the strict and the weak version of comparison really interchange here, right? So it's witnessed before or at the same time. Exists alpha is witnessed before or at the same time as beta. That really means that it's witnessed and there's no strictly smaller witness of beta. And then we have the dual. So if we have this one, then the dual is the dual of exists alpha strictly smaller than exists beta is really that beta is witnessed at the same time as is earlier or at the same time as alpha, right? So in fact, this dual is a kind of strong positive negation. So note that this is simply a syntactic operation, right? And it only works when some sentence of the correct form is given to it as input. So now we use sigma 01 formula in a slightly specific way, namely we only allow one quantifier, one unbounded existential quantifier in front of the delta 00 formula. That's just precisely to get this. So if sigma and sigma prime are sigma 01 sentences, then so are sigma strictly smaller than sigma prime and sigma smaller or equal than sigma prime. Right, so that sigma 01 is preserved under the witness comparisons things. But that only works, of course, as long as you have just one existential quantifier in front and the rest is bounded. Okay, so one quite convenient thing that I'm going to use is self-referential Gödel numbering. So they were invented by Saul Kripke, who unfortunately recently passed away. So the whole idea is that of the self-referential Gödel numberings is that you you really have fixed points. If you look at here of the form phi, and then phi is actually the same as, and not just provably equivalent as psi, and then the substitution of the Gödel numbering, the Gödel number. So it's not, so in the usual Gödel theorem, using the substitution lemma, we have that phi is provably equivalent to psi of phi, and here we have that it's actually equal to it. And it's very easy to define a self-referential Gödel numbering. Simply expand your language with a new constant c, and then you start with a standard Gödel numbering of the expanded language. And what you do then is that you Gödel number phi in the new sense, in that it's the Gödel number of psi, where psi is the first formula in the expanded language, such that phi is equal to the result of substituting the Gödel number or original Gödel number of psi in psi. And then under reasonable conditions, you get that gamma asterisk gives you a unique Gödel number for every phi, and moreover, whenever we have a psi in the extended language, then its literal fixed points exist. Okay, so all this business about the first formula, etc., is a little bit ugly. And I think the main thing is that we demand that Gödel numberings are injective, or are functional in the direction from formulas to numbers. But I think it's not an essential that's not an essential feature of Gödel numbers at all. They perfectly work if you drop that. So if if we drop the demand that Gödel numbers are functional from formulas to numbers, then we can, it's much easier. So now look at the Gödel number now taken in the direction from the number to the formula. That should, be, of course, be functional. So because otherwise the Gödel numbering would be ambiguous. And then we can simply define the new Gödel numbering as simply the Gödel the formula that is Gödel numbered by n in the expanded language, and then you substitute the numeral for n for c. So that you see, if you drop the functionality from formulas to numbers, then the construction of the self-referential Gödel numbering is a piece of cake. Okay, we will use that later. Okay, so now, these were the preliminaries, and now we get to the real stuff. And so the first thing is that we are going to produce an essentially hereditarily undecidable theory, and this is the one that was discovered by Tasky, Mostovsky, and Robinson. And it is the theory Q. And so the axioms of Q are first Q1, Q2, Q3. And those axioms are that 0 is not a successor, successor is injective, and every number is either 0 or a successor. Now these things, at least I found it illuminating to realize that these three axioms together say that successor and 0 are taken together, are jointly injective, and 0 and successor taken together are jointly surjective, right? So this simply tells us that 0 and successor are jointly injective and jointly surjective. And then for the rest, we have the recursion equations for addition and multiplication. So an important observation that is that if we drop Q3, then all the axioms are true in real closed fields. And real closed fields, the numbers bigger or equal than 0. So to take the theory of real closed fields and restrict it to the numbers that are bigger or equal than 0, then all the axioms except Q3 are true, and that theory is decidable. So without Q3 we wouldn't have the undecidability, etc. So this is a kind of really essential axiom to make the whole thing work. And now we will need three important properties of Q, namely, if sigma is true, then Q proves sigma. If a witness comparison is true, then Q proves the negation of its opposite, right? So if sigma is witnessed strictly before sigma prime is true, then Q proves that it's not true that sigma prime is witnessed strictly before or at the same time as sigma, and similarly for the other two. In fact, I think for every purpose you only need one of these two items, but then you really have to remember which. So I cannot remember. So if we really would want to work with 1 and 2, I never can remember then which one I choose. So I think it's better to choose the three properties here instead of just the first and the second, for example. Okay, now we will show that Q is essentially undecidable and hence essentially hereditarily undecidable since it is finitely axiomatized, right? So look at it, it's finitely axiomatized, so we can conclude the essential hereditary undecidability of Q from the essential undecidability. And now it becomes essential that we use self-referential Gödel numbering. So first, since consider any RE extension of Q in the same language. I should have said here. Of course, that's always important. Now consider any formula. Take box phi, let that be a sigma formula that represents sigma 01 formula that represents the provability in U. We know how to do that, right? And so note that we are here talking in the meta language, right? We're talking about truths in the natural numbers. So so in the very weak series, you do not have all the transformations that transform a sigma 1 like representation into in one that has the strictly the prescribed form. But here we don't need the formalized version of the reduction of the natural provable phi to the sigma 01 formula. We can do that externally. So take this formula that represents provability in U, and now we simply take the Russell sentence, and here the Russell sentence is precisely of the form that the negation of it is provable before or at the same time as it, right? And then you can reason as follows. And so this is again this reasoning is not in the theory, it's important. This is in the meta theory, which is something like, let's say, elementary arithmetic plus sigma collection. So that's a kind of very convenient meta theory to do this kind of things in. Suppose that you have the provability of rho, then so we have this, right? And so if rho is provable, then either so if rho is provable, there's a witness of provable rho. So either there is a witness of box not rho before it or at the same time, or not, right? So if that is true, we have rho, and if that is not true, we have rho opposite. So from box rho, we have rho or rho opposite. Now, if we have rho, then we have by definition box not rho, and hence we have the series inconsistent. Quad non, right? We are assuming. Sorry. I should have said consistent RE. The theory U is consistent, and so we don't have this. So if we have the opposite of rho, then we apply this one. So then we have then we apply this one, right? So you find from that box of the negation of rho. And so again, we have box falsity. Okay, in a completely similar way, if we assume box not rho, then we get also box falsity. So we have proved Russell's theorem on very, very weak assumptions on what Q can do. And hence we have proven that that Q is incomplete. And hence, okay, sorry, yeah. So since U is so every theory above U is incomplete, and from that it follows that these theories are undecidable, because if if a theory was decidable, it also would have an RE complete extension by a simple argument, and that's impossible. And so we have the essential undecidability. And from the essential undecidability, it follows that we have essential hereditary undecidability. And so Q is the primary example, the primary example also in Tarski, Mostovsky, and Robinson, that classical book. Let's see. I have it here. Oh. We have to hold it so that you can see it. I cannot. Yes, now you can see it, right? So, yeah, so this classical book that really everyone should have read really introduces Q and its important properties. Okay, so now we turn to a theory R, and we turn to a theory R, and I will, so now the aim is to show that R is essentially hereditarily undecidable. And we will see that R is a theory that is not finitely axiomatizable. And so the lemma that we used to prove that Q was essentially undecidable will not work. Okay, so yeah, here's a little bit of history. So Alan Cobham proved in 1975, so 4 years after the Tarski-Mostovsky-Robinson book, that R is essentially hereditarily undecidable. And his proof is annoyingly in somewhere hidden in the correspondence between Tarski and Vogt. So as far as I know, this Tarski correspondence is not accessible, at least not, you can, I emailed Mike Beeson about this, and he said, well, you should go in person to the Berkeley Library, and there you should first make an appointment, then and prove that you have some real interest in seeing the correspondence, and then you can go to that appointment, and then there will be a librarian looking over your shoulder that you are not treating the things wrongly, and then there's 4 big boxes of letters, and you have to search through them for what you want. So, yeah, so at least for me now that is impossible to do. So I never saw this correspondence. So Vogt in his paper says teasingly that there's very deep ideas in Cobham's correspondence that are not in Vogt's presentation of the result. And so, yes, so one really would want to see what Cobham did precisely. But yes, it's at least at the moment, it's inaccessible. And a year later, Cobham used this result to show that the theory of finite groups is hereditarily undecidable. Again, that proof is hidden in the correspondence with Tarski and Vogt, unless Cobham published it somewhere, but I didn't discover it. So again, I never saw it. So fortunately, Robert Vogt was quite interested in it, and he produced, my guess would be a simpler, completely new proof in 1962. And okay, yeah, so so the proof I'm going to present you shares features with Vogt's proof, but the thing is that what I will do is only use what is strictly needed. So yeah, when I was preparing these slides, Jon alerted me that Taishi Kurahashi also had just published a preprint uh, in an archive preprint in which he provides a proof that again shares a number of features with what I'm going to do in this talk. So, so it's quite interesting, of course, if you look at the timeline, 53, 57, 58, and now, and then 62, and then a big jump of very little interest in this, and now the last 10 years, I think that that interest in R and the wonderful features of R has re-emerged again. Okay, without further ado, let us have a look at what R is. Yeah, the language of R is the usual language of arithmetic. We define t smaller equal u by x. There exists x, so it's x plus t is u for any terms t and u. And then we have the axiomatization. Now, yeah, before we look at this, so I think it's better, it really would be better to have the ordering as a primitive and then some action that says that the primitive smaller or equal satisfies the definition, because very often you want to look at extensions where the ordering is primitive. But yeah, I'm now following the classical, that this is precisely the classical definition from Tarski, Mostovsky, and Robinson. So it really says that the sum of two numerals is the numeral of the sum. The product of the numerals is the numeral of the product, and the theory proves all numerical inequalities, and it proves that if x is smaller than n, then x is one of the numbers, the standard numbers below n. So that's the important axiom. And then we have the R5, the axiom that says not quite that smaller or equal is a linear ordering, but it does say that if one of the components is a standard number, then it behaves linearly. Now, it's an important observation. I think this, so I didn't quite prepare. I think this observation is by fault, if I remember it correctly, but I'm not completely sure. So it's an important observation that we can drop R5, so everything works even without this R5 effect. R5 is interpretable in R1 to R4. So that's the theory R0. So, but I will work in R, but you can keep in mind that you can drop this axiom. It's easy to see that again that you cannot drop R4 because R1 to R3 are again true in real closed fields, and so they do not give you an undecidable theory. So Kripke notes that, so I think he calls R1, R2, R3 the theory school, because that's what we learn in primary school. And Kripke proves that still there is a property of the first incompleteness theorem that is preserved over these three axioms, interestingly. So even this thing, even if it's decidable, still has some interest from the standpoint of the incompleteness theorems. Yes, okay. But so yeah, so this is the theory R. So note that R is very simple, and an important property of R is that every finite subset of the axioms is true in a finite model. So so in other words, R is locally finite, and uh, and that immediately also proves that it's not R is not finitely axiomatizable. Because suppose it were finitely axiomatizable, then it would have a finite model. But since it clearly, because of R3, cannot have a finite model, since there's should be R3 tells us that in the domain of the model there should be infinitely many things corresponding with the standard numerals. We have a completely for free a proof that R is not finitely axiomatizable. So usually the proofs of non-finite axiomatizability are substantially more complicated. For example, try to prove that Presburger arithmetic, so the true theory of addition, that's not finitely axiomatizable. You really have to do the quantifier elimination to prove that. And so so it's kind of bonus that it's so simple here. But now the nice thing is maybe here, right? So if you look at this, right? So think of what could a model of R look like? Right, and so the whole point is that in that model you will have these numerals, and we will have this ordering relation, and so the whole thing is that below such a numeral, the world looks. We just have these things, and addition and multiplication, everything works as usual there, right? So if in such a model we have a numeral of an object corresponding to a numeral n, below it, everything behaves like as it would do on that number considered as a model. And since that is true for every n, so we would have below the numerals, we would have an initial part with respect to small or equal. That is simply omega, right? So the omega is really sitting inside R, and so that's an important thing. And so now suppose that sigma is true. Now then it has a standard witness. And then R will prove sigma. Why is that true? Because for the standard witness, so if you think about the sigma sentence, so all the quantifiers are bounded. If you have the standard witness, then so maybe we have some terms in it that stick out, but they can never stick out more than standardly high. And so So the whole thing reduces to the provability in R of sigma reduces to the standard part that you can see in R, and hence it proves sigma. And similarly here, right? So if sigma is smaller than strictly smaller than sigma prime, then sigma prime has a non-standard witness. And so the insight that not sigma prime smaller equals sigma is really the whole question really plays on the standard number of the standard part in the standard numbers, and so R proves it, right? And so we have these things. But now let's go back to Q, right? So we have, we assume that we have this self-referential Gödel numbering. So we only use these properties of Q, nothing else. So we didn't use the fixed point lemma, or we didn't really use anything of Q than just that it verified these three possibilities because this identity was handled by the self-referential Gödel numbering, and all this reasoning is in the meta theory, right? In, let's say EA plus sigma collection. So so all this reasoning also will hold for R. And hence we will conclude that R is essentially undecidable precisely by the same reasoning as in the case of Q. So that's the essential undecidability of R. Now let's take a step back, and now we want to show that R is hereditarily essentially undecidable, but we already have seen that it's not finitely axiomatizable. So how the hell can we do it? And there is we have the following strategy. So if R is consistent with the theory U, then we will have a finitely axiomatized extension F of R, such that U is consistent with F. So if R, so the whole idea is that R is consistent with U, we can always improve that by that U is consistent with some finite extension of F. And hence, since this finite extension is essentially undecidable and hence essentially hereditarily undecidable, it will follow that U cannot be decidable. Okay, so that's what we want to do. Okay, now, so now think of ourselves as roughly working in R, and let's say that Z is a good number, or good number Z, and we define it as follows. Namely, first, small or equal is a linear discrete order for all the y's that are below it. 0 is the least element of this number, and successor coincides with the successor of this linear discrete order. Yes, and of course for the elements that are below Z, right? So because only there it makes sense. And we have the recursion equations for plus and times, but again for all arguments smaller equals Z. Now we note that by the arguments I just gave, that for every standard numeral, R will prove that the statement n underlined is a good number, right? So R will know that every standard number of every R will know of every standard number that is good. So I think that's a kind of crucial property. Okay. Now we want to define something like the theory of a number, and now we are going to reflect a little bit more about what will be the theory of a sigma sentence. So I write this by the sigma sentence between square brackets, and so you would naively think that this should look like this, right? Sigma, the theory of the sigma sentence is simply that there is a good number that witnesses the sentence, right? So the sigma 0 is the delta 0 internal part of sigma. So why is this not good? Well, the reason is that sigma 0 could, for example, be of the form exist y x plus 3 times x plus 1, y smaller than x plus 3 times x plus 1, such that sigma 1x, right? So the point is, so the witness could still be above above the thing that we want to be a good number. So that's yeah. So that's sorry. The witness, the internal witness here could be bigger than our existential thing, right? So it could stick out, and it's more general than that. It could, because here inside sigma 1 we could still also have terms in another variable, but also these terms, because the value ranges of these terms are also below so the inputs are below x, but the value ranges of these terms could also stick out. So so this doesn't quite work. So what is the solution of that? Well, in my paper, I didn't see Taishi Kurahachi's recent paper, but one strategy is to simply demand that your sigma sentence doesn't have this, right? So we demand that all bounded quantifiers are bound, that the bound is always a variable and not a term, and also that the terms only occur in the simple form x u plus v is w. So we could ask that the sigma sentence is what I call pure, that it has a kind of standard form and not the usual one. But that's but then you have to develop this whole idea of pure things, and so the other thing is simply to ask for a witness that is a good number, but that is sufficiently above x. So I think that's the real idea that we want to. So the theory of the sigma sentence tells us that there's a good number that's sufficiently above x that represents that is the witness, and so that all the in the sigma 0, all the values of terms occurring in the sigma 0 will be bounded by this z. That this z will be strictly larger. And now then you simply sit down and think about, so how large should it be? And fortunately it's not too large, right? So the thought experiment is simply assume that this whole formula would be spent to define a maximally large term, right? That we could use everything here. So then that term would be a big product. But of course, the big product would not grow sufficiently if x were 0 or 1. So we also need that it's x plus 2. And so if we would take x plus 2 and then a big product, so the number of symbols of sigma times, then we are certain that no term in given x, no term in sigma 0 can reach up to that big product. So we say exists z, exists u smaller than z, because below z everything works as normal, as we know and love from the natural numbers. And so then we demand that x is sufficiently small, that's this, and then we say sigma 0x, and so then we get, of course, that that we get the sigmas, we get the truth of this thing if and only if the sigma sentence is indeed true, right? So that's the representation. And so okay. So but the main thing that you want to remember here is simply that we really do this, but then to solve the problem of the terms that are possibly sticking out, we take the witness a little bit larger. And so fortunately it need not be all that much larger that we can easily say this. Wait a moment, I have to close my door. Yeah. Okay, so homework for the Chinese students really proved by induction that my trick works, that the bound that I found really exceeds all the possible values of all the possible terms in sigma. Okay, so then so the important thing is this. So if sigma is false, then every model of sigma will have the standard model as an initial segment. And so it follows that sigma extends R, right? So if this series of a number if sigma is a false sigma sentence, right? So then this series will have, so think of a model of that series. So it will behave like the natural numbers on omega, right? By this definition, and so so it will extend R, and it will have So that's the main point. So and this is a finitely axiomatized theory, right? Because we simply say that there exists a sufficiently large good number sufficiently below which the sigma sentence is true, and so we have that we have a finitely axiomatized extension of R. That's the important point. Now, suppose, consider any U in the arithmetical language. So, and suppose that U is consistent with R. Then, for every true sigma, we have that U plus R proves the theory of sigma, right? Because the theory of sigma is, because the theory of sigma really says simply that there's a good number sufficiently above a witness, but this witness is standard, and you see that then we can compute in R this. The U will also be a standard number, and so the theory sigma also will be true, right? And so U plus R, so R will prove, for the true sigma, R will prove the theory of sigma, and so a fortiori U plus R proves this theory, and specifically, since U is consistent with R, U plus the sigma for a true sigma will be consistent. Right, so that's point one. Now suppose that U is inconsistent with sigma for every false sigma, suppose that were true, then we would have that for every that sigma is false if and only if U proves the negation of sigma, right? So if it's true, U plus sigma is consistent, so it does not prove the negation of sigma. And if it's false, by assumption, it would prove the negation of sigma, so it's false if and only if not sigma. So that would mean that we can decide sigma 1 truths, right? So we simply would simply search search for a witness of sigma, and we would search for a proof in U of not sigma. Also standard assumption is, of course, that this is an RE theory. So we could prove, and so if we find a witness, it's true, and if we find a refutation, it's false. So we could decide this, and ipso facto, we could decide the halting problem, and that's, of course, impossible. So this means that there is a false sigma sentence with which U is consistent. And so let's call that sigma star. So sigma star extends R, and so since R is essentially undecidable, so sigma star is essentially undecidable. It's also finitely axiomatized, so it's essentially hereditarily undecidable. And at the same time, U is consistent with sigma star. That's what we proved here. And so U is hereditarily undecidable. So U is undecidable. And so we have proved that so whenever U is consistent with R, then it's consistent with some sigma star, and hence it's undecidable. And so whenever U is consistent with R, it's undecidable. And so we may conclude that R is essentially hereditarily undecidable. So that's the whole idea of the proof. So maybe it's good to take one step to really walk you through the steps again. To that, I'm sure. So the important thing is, of course, to understand the structure of the argument. Okay. So So the important thing is that we have developed. So the central notion is this, right? So the theory of a sigma sentence, and the theory of a sigma sentence is really the theory that says enough about numbers to evaluate the sigma sentence. And so the important point is that if the sigma sentence is true, the theory has a finite model, and that finite model is in some sense simply a big number, right? And okay. And the whole thing is that the important observation is that if sigma is false, then this theory could still be consistent. But what I'm claiming here holds even if it's inconsistent. So the theory of the number sigma really always extends R, right? Because the fact that the big witness is good makes that it behaves like R on the standard part. And so the theory always extends R. And now we get the argument. And so the argument really says that we always can find an extension of R that is consistent with U, right? So suppose U is consistent with R, then we can find an extension that is consistent. And that extension will be the theory of sigma star, where sigma star is some false sigma sentence. So now how does that work? Well, if it's true, if the sentence is true, then the theory of the sigma sentence is consistent with U. Really, because R proves it, and the theory is consistent with R. Now, if to get a contradiction, we would assume that the theory is inconsistent with every false sigma sentence, it would follow that that we could decide sigma 0, 1 truths. That's we know since Turing that cannot be done. So a contradiction. So there must be a false sigma sentence that does the trick. Of course, I think this is an extremely convenient way to do this. But of course, by investing a little bit more time, we could also concretely, so if we have an index of U, we could really concretely find this sigma star, right? So the argument as I gave it is not very constructive, but we could of course make this completely constructive to find this sentence that is consistent with U. So now, okay, now then the finale, right? So we find this finitely axiomatized theory that extends R and that is consistent with U. Since it extends R, it will be essentially undecidable, since, as we already saw, R is essentially undecidable, and it's an extension of R, and essential undecidability, by its very definition, will be preserved to RE extensions. So it's also finally axiomatized, and so by this very old argument and trivial argument due to Tarski, Mostovsky, and Robinson, it is also going to be essentially hereditarily undecidable. So now, but we also showed that, we found sigma star in such a way that this is going to be consistent with U, and so it follows that U is undecidable and even hereditarily undecidable. So, and now we started assuming, where is it? I started assuming this, right? So U is consistent with R, and we concluded that U is undecidable, and that's precisely the characterization of essential hereditary undecidability, and hence we are there. So yeah, I hope that the whole structure of the argument is now clear. Okay, so now let's see. Yeah, I'm still faster than Young wanted, but I don't think it's too bad when we stop a little bit before time. So one question one could ask is the following, right? So you would, so what the question, so as I put it here, it's incorrect. So what you would hope is that in a sense, take any essentially undecidable theory, you would hope that it's essentially hereditarily undecidable if there, so I should have said, if there is a subtheory U0 of U in the same language, no, the whole thing is scrambled anyway, I see. Okay, let me try to say it in words. So what you would hope is, so all the theories like piano, arithmetic, etc. Inherit this property of R, right? Because since everything that is consistent with an extension of R is ipso facto consistent with R itself. So you would hope that this phenomenon of essential hereditary undecidability could be reducible to could be reducible to this kind of thing, right? So we could hope that the theory is essentially hereditarily undecidable if and only if it has a subtheory, let's say U prime, so that every theory that is consistent with that subtheory is consistent with a finite extension. So that's what I should have said here. I will repair the slides and send them to Jon so that you can read the correct statement. And in fact, abstracting away from the specifics, for the case of R, we proved the right to left direction. But it turns out that there are essentially hereditarily undecidable theories that are completely unlike R or extensions of R. So William Hunt provides an example of a theory H, that is H for Hunt, that is essentially hereditarily undecidable, but is inconsistent with any finitely axiomatized, essentially undecidable F in the same language, right? So that theory can certainly not have some subtheory that has extensions that are finitely axiomatized and essentially undecidable. And so, one would have hoped that the thing with R would be a kind of pattern that recurs, and that essential hereditary undecidability is in some sense deeply connected to R. But it turns out, due to Hans' example, that's not the case. And so this is really something that happens all the time if you think about not only about this notion, but also this kind of notion like effective inseparability of series, etc. So for almost every generalization you think of, that turns out to be a counterexample. And so in some sense, the landscape of Gödel 2-like theorems is in some sense extremely rich and many-colored. Okay, yeah. Okay, we can even go. We can even go one better. So there's a property that seems to me to be stronger than effective inseparability, than essential hereditary undecidability, and that's what I ad hoc call strongly recursively or effectively inseparable. So we say that the theory is inseparable if the theorems of U and the phi of the U language that are refutable in predicate logic are recursively or effectively inseparable. So you take the theory, you take its theorems, and you take the things that are refutable in predicate logic. So if these two sets are in the same language, if these two sets are recursively or effectively inseparable, then the thing is strongly recursively inseparable. And now Vought shows that R has this property. So I stared at Vought's proof for a number of times, and he has this notion of existential interpretability that is central to his proof, and I'm still wrestling with the details to verify whether that notion really works like Vought thinks it works. So I'm still not quite sure about Vought's proof, but on the other hand, it's Vought, right? So we should be able to trust him. Fortunately, thinking about it, I also found different proofs. Now, in fact, today I got an email by Taishi Kurahashi in which he sketched yet another proof, different from mine, and again different from Vought's. So there's already two independent proofs of the same thing, so we can be fairly sure that that's true. And this strong effective inseparability does in fact implies hereditary essential hereditary undecidability. So why? Well, suppose you find there's a decidable W in the language of some theory U that is consistent with U, then we find that the phi's that are refutable in W are a recursive separate of the theorems of U and the refutables in predicate logic, right? The refutables of W extend the refutables of predicate logic, but because U and W are supposed to be consistent, U does not prove any of these refutables. So that's in fact the definition of consistent mutual consistency. And so so since there is no recursive separator, if we assume that U is strongly recursively separated, then there is no such W, and hence any such W will be undecidable. But that is really the definition or the characterization of essential hereditary undecidability. So this notion really implies it and is probably stronger. Okay, so Ehrenfeucht provides an example of a theory that is essentially hereditarily undecidable, but not recursively inseparable, and hence it's also not strongly recursively inseparable. So we really have an example that shows that this notion is a stronger notion than essential hereditary undecidability. So what I don't know is, so I haven't spoken about, and in fact, I'm not completely sure about the right definition. Of course, we could want that this notion is also in some sense have an effective version of it, right? Where we do not, so if we have this consistent theory, we provide a witness of its undecidability somehow effectively from an index or something like that. But I'm not completely sure about the right definition here. So what you really would want to say is that some effective version of this is yes or no the same as essential strong effective inseparability. So so there is still some work to do here with the counterexamples. But if we do not ask for such effectiveness and simply look at recursive inseparability and the recursive version of this, then certainly we do have a separating example. And let me just say that that's also a kind of small Ehrenfeucht example is also a small jewel. So it's a beautiful example, but regrettably, of course, I can't treat it here.
Thank you, Professor Visser, for this very wonderful lectures. The main content of this lecture is to give the proof that the theorem R is essentially hereditary undecidable. And in history, this theorem was first proved by Cohen, but he didn't publish the proof. And later, Volt gave proof. In this lecture, which is mainly for our student, he presented a new proof of this important theorem. And in fact, in his published paper on Q, he also gave a proof of this theorem. But in this talk, the proof he gave does better than any proof in published paper in the literature. Okay, we still have time for the comment or questions. So any question from the audience are very welcome. So anyone have answer the Professor Munir has a question. Okay.
You can all people. Those Chinese students can also ask the questions in the chat if they want.
Yeah. Any question is welcome from our audience. At here or the audience at the 学识之平台. You can post your question at the 学识之平台 and the officer can forward the question to us and post here. Okay. Any questions? Okay, we can wait for a minute for the possible questions. In fact, we invite one colleague to do the interlocutor work, but unfortunately he has teaching, so cannot attend this lecture. And yeah, I can I can do some anyway kind of work, and I hope I hope this it's helpful. So in fact, I have a few slides to share. Could you first close your slide and so I can share? Yeah.
Well, which, okay, I'll stop my slides. Wait a moment, so. Stop share, yes.
Yeah.
Yes.
Okay, I try to share my slide. Yeah, I hope all of you can see. Yeah, I just some small comment for Professor Visser's talk. The notion of essentially hereditary undecidable zero was introduced by Kasky, Mostowski, and Robinson in the classic book Undecidable Zero. And in this talk, Professor Visser gave a nice equivalence of this notion. A zero U is essentially hereditarily undecidable. Is equivalent to that for any zero W in the U language. If U plus W is consistent, and then U is undecidable. So this equivalence from the Visser is very useful. Just you only to show this. It's well known that Q is essentially hereditarily undecidable. Because any zero in the same language with U, which is consistent with U, is undecidable. This is well known. The zero R introduced by Kasky, Mostowski, and Robinson in the book Undecidable Zero is a good base theorem for studying incompleteness and undecidability. So this theorem is very important and useful. This is also the main topic of Visser's talk. So that is very important. And Cohen proved that R is essentially hereditarily undecidable, but he didn't publish the proof, and Vogt gave a new proof. And just also say that in this talk, Visser gave a new proof based on Vogt's proof. In fact, in his paper on Q, he also proved the same result using the theory of number Tn and the interpretation. But the presentation of the proof in this talk does better than no proof in the literature, as you can see from the proof in this talk. And the key idea to prove this result that R is hereditarily essentially is essentially hereditarily undecidable is to show that if R is consistent with a zero U in the same language, and then this U is consistent with a finitely axiomatized extension of R. So this is the key idea for Visser's proof. And this result for me is very important because it provides us an important tool to prove undecidability. For example, if you can find a zero is in at least the same language as R, such that it is consistent with R, and then we can get that this R is undecidable. So this result is very useful. But Hans give an example of a zero that is essentially hereditarily undecidable, but inconsistent with any finitely axiomatized, essentially undecidable zero in the same language. So this is uncountable. This counterexample is very important. Also, Visser talked about this. In fact, the theorem R has many nice and important mathematical properties. For example, any theory interpreting R has strong mathematical properties. For example, any theory interpreting R is effectively inseparable. So theory interpreting R is very strong in this sense. But the Euro mathematical property, for example, effectively inseparability does not imply interpreting R. So for me, but you may don't agree with me. For me, that the R is the weakest natural theorem, such that G1 holds for R, or that just the weakest natural theorem, which is essentially undecidable. In fact, Visser has also made other contributions about the property of the theorem R. For example, he proved the following very important, very beautiful theorem. These theorems give us a characterization of what kind of theorems can be interpretable in R. He proved that for any RE theorem with finite signature T, T is interpretable in R if only if T is locally finitely satisfiable. Here is the definition. We see that T is locally finitely satisfiable just means that any finitely asymptotized subtheorem of T has a finite model. So this theorem is very nice. Give a characterization of series which are interpretable in R. Furthermore, we can examine the relationship among these mathematical properties. In fact, in his lecture, he also mentioned this. For example, T is essentially undecidable does not imply T is essentially hereditarily undecidable. I just denote this notion by EHU, and T's Ri does not imply T is EHU, and T's EHU does not imply T is Ri. Ri just means recursively inseparable. T's EI does not imply T's EHU, and T's EHU does not imply T's ER. Also, in his recent reprint, essentially hereditary undecidable series, he shows that there are EHU series which is strictly below R. In fact, for any just RE degree, for any non-recursive RE degree, we can find a finitely EHU series with the same degree. This can be found in his new the recent preprint in Utrecht. And the study of the mathematical property of formal theorem provides us a uniform and abstract way of studying incompleteness and undecidability. And Visser has made important contributions in this line of research. Okay, if no one has currently have no questions, in fact, I also found maybe three questions. The first question is not about the proof of this theorem, it's about the application of this theorem. In fact, I don't know this theorem. The definition of EI is very low. It's about say T is EI, just means that the set of sentence provable in T and the set of sentence is refutable in T. This pair of sentence is EI. But in your talk, you propose the notion of strongly effective inseparable. I didn't know this. My question is not about the proof of this T theorem. My question is that what is the motivation to consider the set of sentence which is refutable in predicate logic, not just the set of sentence refutable in T. So for me, that the definition of EI is very natural, but I don't know what is the motivation to consider this set of sentence refutable in predicate logic, not in a given theorem T. Also, I don't know what's the application of this theorem? Just I believe it's important, but I don't know about this application. So maybe you can say more. Yeah. The second question that do you think what's the most important open question about R? Yeah. Yeah. Maybe just these two questions. Okay, that's all. And
okay. Let's see. So, yeah. So the question about the strong inseparability. Yeah, I think the important point there is that the ordinary recursive inseparability of two series doesn't is in some sense incomparable with the is incomparable with the hereditariness, right? So the interesting thing is that this other notion with the empty theory on one of the two sides and R on the other side, that does imply that happens to imply the essential hereditary undecidability. So it's clearly a stronger notion with a lot of further consequences. And in fact, the example of this example due to Hanf also uses the following insight that if you have a theory and you have a finite subtheory, and the refutables of the one and the theorems of the other, it doesn't matter which is which, are recursively inseparable, then it's essentially hereditarily incomplete, right? So it's not just the empty theory, but if you have in the role of the second an empty, a finite subtheory, it's already gives you this kind of stronger property. And so Hanf used this in his counterexample. So it's, yeah. So I don't know whether it has a kind of important applications outside of this area of thinking about forms of incompleteness, but definitely, for example, this kind of thinking led to Hanf's counterexample. And in fact, the notion itself, so Volt didn't give him a name, but I think Volt invented this phenomenon, right? It's his strengthening, in fact, of the Drachenbrot theorem that we were looking at. Yeah, so the Drachenbrot theorem is, I think, one of the first results of finite model theory, right? So it's so the whole point is that the sentences valid in all finite models are complete by 0, 1. And so that's a founding thing, right? So that the insight that finite model theory really behaves quite differently from behaves quite differently from the usual model theory. So yes, so undoubtedly, Drachenbrot theorem has other applications in finite model theory, but I don't know them because I'm not really, never really studied finite model theory. But I think this basic result that these things are by 0, 1 complete. That's of course quite thing, because you know the theorems are pi 0, 1, and so the complement is sigma 0, 1, and so if you could recursively separate these things, then that would contradict the theorem that I showed to you, right? So the complete pi zero oneness of the finite the series that are true in a finite model is an immediate consequence of the theorem, and that last theorem is really known as that's the most well-known form of the Tatenboom theorem. The most important question about our I'm not sure about that at this moment. So R is one of the few theories that can be characterized in terms of degree structures of interpretations. That's of interpretability. That's of course that we have, and and R's behavior with respect to this essential hereditary undecidability we also have. I'm not completely sure what now would be the most urgent question, but maybe it's also up to you and the new generation to ask that exciting question. So I think that the real interesting question would be to characterize Q, right? So can we find characterization in terms of degree structures of Q? That would be something to do. And because Q is extremely natural, right? There are so many series mutually interpretable with it that are quite natural, like S12, all kinds of series of strings, all kinds of finite set series, so that they're all the same thing as Q. So Q is a quite natural notion. It seems from experience, but nobody could characterize Q in external terms, in terms of some degree structure. So that would be the next. That would be a real great project.
Okay, thank you. Yeah, by the way.